Yes, today we're going to talk about acid-base neutralization problems. So, one thing about acids and bases, because they deal with hydrogen and ultimately hydroxide, it may not be a base that has hydroxide in it, but it's going to cause some hydroxide ions to be made. Those hydrogen, those protons, and hydroxide ions can actually meet up with each other and form water. And that's called a neutralization. So when we put two things, one that's an acid and one that's a base together, there can be a chemical reaction that happens. So let's take a look at that. A simple acid-base neutralization problem would involve hydrochloric acid and sodium hydroxide. Okay, now if we look at our sheets, hydrochloric acid is a strong acid. It completely dissociates, it completely, we say, deprotonizes, and we get out, of course, so a one-way arrow because it is going to completely dissociate. We get out the H plus ions and the Cl minus ions. Likewise, sodium hydroxide is a strong base. It's going to completely dissociate. We get out sodium ions and hydroxide ions. These two things really like to find each other and form water. Now, of course, we know that technically the H plus isn't a hydronium, an H3O, but that hydronium, it's not real happy to be hydronium. It would love to give up that hydrogen, give it back to an OH, and create two water molecules instead of a hydronium and a hydroxide. And so that's what's going to happen in these situations. Now, if we put both of these things into the same solution, into the same beaker, then those things are going to be able to find each other. But we need to rewrite this equation then a little bit. So what we actually are going to do is take the HCl and the NaOH, we're going to put those into the same solution. They're going to deprotonize. They're going to form their ions. And we get out H2O, and then the Na, the Cl in ionized form. Okay? So those hydrogen ions and those OH ions that would have been in solution otherwise, would have just been floating around there, creating it to be very acidic or very basic, they have met up and they've formed a water molecule. And because they've formed a water molecule, then those two things are not going to be contributing to the pH. Because, of course, the water molecule doesn't have anything to do with the pH when it doesn't have an extra hydrogen on it. So by putting these two things together, if we had two solutions of these separate, we would have, something with a high pH and something with a low pH. That pH is now changed. It's become neutralized because those OH ions and those H plus ions have been taken away. Now, if we had equal amounts of these two things, then it would be completely neutral. It would completely neutralize each other. The H plus ions and the OH ions would kind of all find each other, and we would get a solution that has a pH of 7. But in most cases, that's not going to happen. You're going to have a little bit more acid or a little bit more base, and the pH is going to be off of 7 a little bit, but it's not going to be as strong as it would be in the original solutions. Now this NaCl, we know because they're in solution, these things have to be ionized. Okay? They have to be apart, surrounded by water molecules. But a lot of times we just kind of gloss over that fact, and we write it as NaCl. Now most of you probably know NaCl is the chemical formula for table salt. So we write this out like this. This would kind of be what we call the summary equation. Because if we were to evaporate all the water off, then you would just have salt left. So in a neutralization reaction, what happens is we have an acid plus a base gives us water plus a salt. Now, NaCl is what we normally call salt, but that's a specific type of salt. Really, in the chemical sense, a salt is any type of ionic compound. So we could just as easily look at a situation like this. Let's go HBr plus, let's do potassium hydroxide. In this case, we would still get water out, and we would get KBr, potassium bromide, but this we would still call a salt. Even though it's not the salt we're used to, any type of ionic compound that is formed is going to be a salt. Now, in an acid-base neutralization problem, we should be able to figure out what the resulting pH would be after the two things are mixed together, even if they have different concentrations and different amounts. So let's go back. I'll rewrite it up here, our summary equation. We're going to stick with the NaCl as the salt. We have to actually start with our sodium hydroxide. That's going to give us water. And table salt. And it's true, hydrochloric acid, which is a strong acid. I mean, if you put hydrochloric acid on you, it will cause skin irritation. It is the acid that is in your stomach, of course, and that's going to help break down your food. Sodium hydroxide, which is a strong base, that would also burn you. Burn is not a great term there. It's going to corrode you, but it would cause some problems if it got on your skin. When you put those two things together, if they react, you get out water and salt, and if you evaporated the water off, it would be no different than the salt that you put on your food. What we want to look at in this case, let's say we had different concentrations of the NaOH and HCl. Let's say the concentration of NaOH is 0.2 molar, and the concentration of HCl is 0.1 molar. But in this case, we're going to have different amounts too. Let's say that we start off with 500 milliliters of NaOH, and the HCl, we've got a little bit more. We've got 800 milliliters. When we pour those two together, we should be able to calculate what the pH of the resulting solution is going to be. Okay, now, at its basic sense, this is kind of a stoichiometry problem. Now, before you get too bent out of shape about that, this is probably the easiest type of stoichiometry problem there is. We don't really even have to set up the normal stoichiometry stuff. So let me show you what's going on here. First thing we need to do is figure out how many moles of each thing of these things we have. Okay, we've got a 0.2 molar solution. Remember that molar means that's how many moles per liter there are. We've got 500 milliliters of it. We have to remember, of course, that that is 0.5 liters, and the 800 milliliters would be 0.8 liters. So in this case, we can set up a dimensional analysis here to show it. If we take 0.5 liters of the NaOH, and we put it in as 0.2 moles per liter, here the liters will cancel out. If we multiply, that'll tell us how many moles of this we have. So all you really do is take the molarity, 0.2, times the volume, 5. We get that there's 0.1 moles of the NaOH. We do the exact same thing for our hydrochloric acid here. So 0.8 times 0.1, so we get 0.08 moles of the HCl. Now, which one of these things is going to be the limiting reactant? Well, it's got to be the hydrochloric acid. We don't have as many moles of that. For every 0.1 moles of NaOH, there's only 0.08 moles of the hydrochloric acid. And actually what we're calculating here is how much we absolutely have. So that means the hydrochloric acid is going to get used up first, and there's going to be a little bit of the NaOH left over. And so that should tell you right there, we're going to have a basic solution when we're done. It's not going to be as basic as if we just had the 0.2 molar solution to begin with, but it's going to still be a little bit basic because there's just not enough hydrochloric acid to react with all of the NaOH. But figuring this out is pretty simple. How much of the NaOH is going to be left over? Well, if we have 0.08 moles of it that will react with the HCl, and then that's going to be gone, what would be left over is 0.02 moles of our NaOH. Ultimately, we want to find the pH of this solution. So we're going to have to find a concentration. We need to put this back into a concentration by taking the number of moles and dividing by the volume. We put in 0.5 liters of one solution and 0.8 liters of the other. So the total volume we have here is 1.3 liters. So to find our total concentration, we just take the number of moles divided by the total volume. And that gives us 0.01538. We'll take a couple extra decimal places for the math here. And that would be the concentration, 0.1538 molar solution. And of course, that's going to be of the NaOH. Okay, now at this point, that's the concentration of the OH that we're going to find in there. So if we take the negative log of that, that gives us the POH, 1.81. And then we can subtract to find the pH. 12.2, basically. Okay, so these neutralization problems aren't a huge deal. Basically you just want to calculate the number of moles, figure out which of those things is going to get used up first, figure out how much of the other thing is going to be left over, find the concentration of that thing once it's left over, find the pH. And that's what we're working on as far as your homework goes today. We've got a couple of things to talk about before you actually get to your homework. But in your homework problems, you're going to be looking at these types of reactions. Now, if we were doing weak acids and weak bases, before we could do all of this junk, we would first have to do ice tables for each of our compounds. We'd have to do one ice table for the acid. We'd have to do another ice table for the base. We'd have to look at the concentrations of the H plus and the OH minus ions that are actually produced. Put those into this action, figuring out which one's the limiting reactant and everything, and then figure out what the pH is going to be at the end. But there's some complications with that because when they get used up, as we're going to talk about when we talk about buffers, things are going to go and change, and you'll actually get more H plus ions that are released and all that. So that's pretty complex. We're not going to worry about that. Our neutralization problems are always going to be strong acids and strong bases. So we can always assume that they're just going to completely dissociate, and we don't have to worry about calculating those concentrations using ice tables. One other thing that we can look at with this type of problem, though, is the concentration of the salt that is produced, the NaCl. So if we said, here we found the pH, and that's great. We said, okay, what would be the concentration of the salt? How salty would the solution be when we're done? Well, there, what we want to look at is the limiting reactant. Because we know all of the HCl is going to get used up, we know that for every 0.08 moles, we're going to produce 0.08 moles of the NaCl. Okay? Now, how do we know that? We look at our balanced reaction. Luckily, most of these acid-base problems, the reactions balance pretty easily. We haven't really focused on balancing these problems because they're always a 1-to-1 to 1-to-1 ratio. There are a couple exceptions, but those don't come up all that often. And so here, because it is a 1-to-1 to 1 ratio, we don't need to worry about calculating mole ratios. We can just go, okay, if 0.08 moles of HCl were used up, that's how much of the NaCl has to be made the sodium chloride. So if we've got that many moles of sodium chloride and we want to find the concentration of that salt, we're going to do the same thing that we did down here. We're just going to divide by 1.3 liters, the total volume. So our concentration of salt there would just be 0.08 divided by 1.3. So 0.0615 molar. So that's just one little additional step that I believe you'll have to do on your homework, finding the concentration of the salt. But the salt is always going to be just based on the limiting reactant, because that's the total amount that we can actually make. And that does come back to stoichiometry. But as you can see, because of these 1-to-1 ratios and the simplicity of how the acids and bases work, it's not quite as much work as going through the whole acid-base reaction stuff. Sorry, not as bad as going through all of the stoichiometry stuff that we did before. Okay, the last thing that we're going to talk about are buffers. Okay, a buffer is a solution that resists a change in pH. And the way you make a buffer is you take a weak acid or base and you put it into solution with its salt. So as an example, let's look at, say, hydrofluoric acid. Hydrofluoric acid is a weak acid. It's a weak acid really because the fluorine ions are so strong that they're able to keep a lot of those hydrogens bound to them in solution, even though the water is trying to rip them apart. We know it is going to dissociate some of them into H+ ions, F- ions, but because it's a weak acid, it's going to reach some sort of equilibrium, and only some of those will be in solution. Now, if we take that HF, and we put it in with, say, sodium fluoride, then what we're going to get is we're going to get a solution where we have HF on one side. It's going to be creating these H+ ions, so it is going to be an acidic type solution. But on the other side, you're going to have these NaF molecules. And because it's a weak acid and it reaches equilibrium, there's kind of a back and forth that can happen right here. So we know there's going to be H+ ions that are in solution. We know really we should write this out as Na. Well, now let's keep it as NaF so we don't get confused here. Oops. Let's see this over here. Alright, so we've got HF on one side, the hydrofluoric acid on one side. We've got HF+ ions in solution. We've got some of this NaF here. What would happen if we stuck... Morning. Sorry, that was a Manning interruption. All right. So we got this mixture here, and What's going to happen if we add more acid into this? This is in equilibrium right now, right? There's a certain amount of this, there's a certain amount of this, there's a certain amount of this. If we put more acid in here, if it's any sort of thing, let's say we throw in HCl, okay? We know that's going to dissociate into H plus ions and Cl minus ions. What that's going to do is increase the concentration of the H plus ions. And because this is in equilibrium, there's a certain amount of each one of those things. That's going to throw the equilibrium off. And what's actually going to happen is that more of these H plus ions, because there's extra of them in this case, some more of these is actually going to combine with the F, the fluorine ions, and we'll actually get an increase in the HF ions over here. And so because some of those extra H plus ions are going to be taken out of solution by the extra fluorine that will be released by the sodium, some of these will break away and form up with the H plus ions. That means the pH of this is not going to change as much as if you just put HCl into water. It's taking some of those hydrogen ions out of solution, and so the pH doesn't change as much as it could. And that's the whole point of a buffer. The point of a buffer is to be able to have a solution where an acid or a base is put in and the pH doesn't change very much. We can also think about what would happen if we put a base into the solution. Oops. Erase this here. Rewrite our NaF. So let's say we put in a base like magnesium hydroxide. Okay, this should make the solution basic. It should add a whole bunch of these OH and take a bunch of the H plus, extra H plus out. But what happens is, in this case, some of those OH is actually going to get attacked by the H off of the fluorine and will form water. So in this case, we've also thrown off the equilibrium because actually some of these OH are going to go in and combine with some of these extra H plus over here. We've thrown off the equilibrium. Some of these are going to come out. This is going to go down. This is going to go down. And we still have a buffer in solution here. So it can buffer both acidic and basic compounds just because it's able to kind of shift its equilibrium. In one case, it's going to shift so that there's more H plus ions in solution, which will take up some of those extra OH. In some cases, it's going to shift so that there'll be less H plus in solution. So the pH is going to not change as much because there's kind of counteracting measures. And this is why we're not going to do any calculations with these types of reactions, because it's so hard to calculate what the pH is. You have to know how much it's going to shift. There's other calculations that you have to do. It gets pretty complex. So the most that I want you to know is this basic. I mean, really, I don't even care if you're able to write out what would happen here. I was just showing you. This is basically what I want you to know. Buffer is going to be a weak acid or base mixed with the salt so that it can kind of shift its equilibrium and respond to whether it gets extra acid or extra base that is added. And the whole point is that it resists pH change. That's really the majority that I want you to know about buffers. But buffers are really important in chemistry and biology and that kind of stuff. Aspirin is an acidic compound. It's called salicylic acid. And so if you eat a whole bunch of aspirin, it will really change the pH of your stomach, and it can cause ulcers and things like that. It will, even though your stomach is at a low pH, it's kind of at a standard one. So if you put a bunch more acid in there, it's going to lower the pH quite a bit, and that can cause problems. So anymore today, you probably get buffered aspirin. It has a buffer mixed in with the acid so that when it goes into solution in there, it will kind of take out some of those extra H plus ions, and it won't change the pH of your stomach that much. Your body, there's all sorts of biological buffers that'll cause effects like that. In anatomy, we talked about some of those that deal with reproductive system and keeping the pH kind of more constant. Okay, we had another Manning sighting. So anyway, and in chemistry we use buffers all the time. We want to add these two things together so that we get a chemical change But because they're acids and bases, it's going to change the pH. We don't want the pH to change that much. We throw a buffer in there just to keep the pH kind of not neutral. It's not going to keep it neutral, but it will keep it more towards the neutral end than it would be without. So that's pretty much all I have for you as far as neutralization problems. We'll get into using neutralizations for titrations, and I'd really like to be able to do a titration lab before the end of school because they're kind of cool. You can see how you can actually calculate the pH of an unknown acid just by doing a titration using an indicator, and the BRAs are kind of neat to use. So hopefully we'll get to that next week. But for tomorrow, do 14.8. But let's see. I got to look because I don't think I was going to have you do all of those right away. Yeah, why don't you just do 1 and 2 on 14.8? Those shouldn't be too hard. You basically just the simple neutralization problems we looked at. So do those. We'll have solutions tomorrow, and then we'll move on from there.